Hello, crazy people. Volume's too loud in my phone. Last stream was measuring the capacitance of my microphones. This music is so exciting. So I really wanted to come back to this project here because I think today I want to try to actually make this work. I actually want to put a signal on this microphone, and I want to try to hear my voice probably on this little speaker here. All right. Cool, right? Let's see if that works. But before that, I want to try some other stuff. So we have our oscillator. I want to change the music. I should have a better playlist, to know which songs are more dramatic. See if that works. Yes. Is it? It's hard for me to know if it's too loud or not. I still need the proper monitor. Yeah, so we did this oscillator, right? I have to change my battery because I accidentally shorted the previous one. So let's zoom in our old circuit again. So if you remember from a few episodes back, what we have here is the 4047 oscillator. We have this potentiometer here. Allows us to control the duty cycle, right? Yeah, unfortunately the frame rate is terrible, but you can see that one of the LEDs now is mostly on, or the other is off. And I change the potentiometer. Now they are on the same. So now the other LED is on. Yeah. So we have here then 4047 oscillator. This controls the duty cycle, and this is an analog switch 4016, and we have two switches, and I want the first one to be off most of the time, so that's what I want. Yeah. Completely out of frame. I'm not sure I can keep the LEDs here as the circuit's working in the end. But the first switch, this one will connect our capacitor or microphone to VCC. And the second switch connects our capacitor to some resistor, alright? And this whole thing is going to be operating in high frequencies. So that's why first I want to test just putting this like in an audible frequency, so we can test also the speaker. So, to-do list. What's a to-do list? It's so disorganized. Yeah, because first I want to try to just use this oscillator in high frequency. We can also try to measure this, because this multimeter can measure frequency and duty cycle. So I want to see if that really works. And later we're going to push this up to 100 kilohertz. And that's when you're going to put this microphone here as a switch capacitor with this big resistance. This is 100K, which is the same as this. And by the time I do that, I'm also gonna use these tiny capacitors, okay? So first of all, I'll replace this capacitor by this to generate an audible signal. And later I'll put an even smaller that matches this one. And then this capacitor with this resistance will be pretty much the same as this and this, so it's the same time constant for the RC net. The idea is that this resistor and capacitor, this is like charging and discharging, right? So the capacitor is really going from more or less VCC to more or less zero. So that's why we'll just take like the same dimensions there. Anyway, so what I'm gonna do next, I'm just gonna replace this stuff and see if I can create an audible signal from this oscillator. So let's do that. Yeah, so that's it. We can try this already. So you can see the lights are constant. It will explode. Can you hear it? I'll even shut down the music. Oops, accident. It's not in focus. Come on, autofocus. Alright. Okay, we can generate an audible signal. Let's measure it. See if I really can trust this not so cheap multimeter. Where will I sample this? Really should get the alligator thingies. I made this alligator. 4 alligators. Very dangerous. The circuit is running. Oh, you shut it down. Where is it again? This just goes to ground here. Here. Oh. Okay, turn it on. 330 hertz. I think I calculated like for 440, but knowing something could be off because I'm just assuming a lot of stuff about this circuit. And we got 330. Cool, I think that's an actual note. It's 3/4 of an A or La. I think this is an actual note. I won't remember which one this is. 3/4, of course. If you're following a Pythagorean scale, that's for sure a note. But even in the chromatic scale, I think it's pretty close. But I won't be able to make calculations right now for you. If you are a music nerd, you can tell me, let me know in the comments, which note is this? And I think this thing also measures the duty cycle. So let's check. Yeah. 16%. Change here. 6. Oh, cool. Cool, huh? And you can see the LED is going off because it's off most of the time. And focusing is really annoying me. I like my manual lens better. Cool. Yeah, well, that's what I want, pretty small duty cycle. And the red light also, you can see it going brighter and less bright. We're basically dimming it here, right? It's basically a dimmer. Alright, let's hear what happens when you change the duty cycle. You should actually hear different timbre, so the actual spectral content of the wave is changing. Because you go from square wave to something that's more like an impulse train. I disconnected something. I think I shorted something. Let's try. Okay, one more time. That's what rock stars say. One more time. Oh, what's happening? breaking something bad. I don't trust these wires, you know, this. I used to work just with the cut wire straight on the protoboard. These little connectors, they're not good. Well, that's the first time I had any problem, but anyway. Oh, that's cool, huh? Actually seems to be changing the frequency as well. Let's check if it's changing the frequency with the multimeter. Shut up! It's quite possible. It's just a hacky circuit to create this variable duty cycle, but it works. If you need a fine exact control, then you need something different, yes. Cycle changing, right? So back to frequency. 50. Oh, it's definitely going down. It's not a lot. It's an octave. Yes, it's a lot if you in a different point of view. Actually, the minimum somewhere in the middle here. Yeah, so the control, at least with these values here, definitely doesn't hold the frequency exactly as you change the duty cycle. But yeah, if you don't need to really control it and you just need like a constant wave with a very short duty cycle, that's what I need. You just adjust the frequency later, change the capacitor, right? So the circuit is good for our purposes. Okay, so thinking if I can try already switch a capacitor, but I'll just go forward. I will just now yeah, let's make the capacitor even smaller and try if we get to 100 kilohertz, okay? So just make these changes, and I'll also adjust the white balance of the camera. So we'll be back very shortly. when you connect the probe, something happens. So this measurement here is probably not very high impedance. Again, so 160K. That's what I was looking for. Minimum duty cycle now is 16%. Now, like I said, the circuit is a bit of a mess. Maybe I can change the resistor values or whatever, but that should work fine. Actually, the green LEDs are not changing anymore, so that's not such a good sign. Red LED is dimming. The green LEDs are not behaving as expected. Maybe okay, they're good. I have to disconnect again. Forgot the song too loud. Hey. To disconnect this stuff. So, see the green LEDs. Cool. Yeah, let's just go for it. Here's the microphone. Where is it? Yeah, that's kind of the moment of truth here. So I'm gonna play even my favorite song. So the capacitor, the microphone is connected. So the two switches, they are now connected through the terminals. Okay, so now it's like one switch that goes like this. The capacitor is to the ground. The capacitor always means the microphone. The other one is like a resistor to the ground. Yeah, this is the idea. And yeah, well, this is. I'll just turn it on and see if it works. Shut down the audio. Yeah, it didn't work. So maybe I can just put a signal amplifier there. This could be it. This could be what makes it work. Or actually I can just try to put there already in the microphone input from the computer, and that will work. Let's just do it in the next episode. So today we just, I just changed the frequency from the oscillator, so maybe it's enough for today. Okay guys, thanks everyone, see you later.